Hello everyone, this is Aditya and today we study complex integrations in a one shot. So let's start the lecture, but before that please do like, share, subscribe my channel and please support the video. Now let's start. And yeah, I've already made a one shot on complex analysis and conformal transformations. Please do check it out, else you will face problem in understanding all these. Okay, so now let's start. Let's start the lecture with the proof of complex integrations. That how is it done? Well, it is nothing new which you have studied in 12th grade. That is what we are going to do, right? Nothing new. Okay. So in a complex plane, we are defining a contour z of t, and t is called the parameter, right? And we are defining a function f, right? First statement is basically we are defining a function and a contour, right? Okay. Now let P be this set. Okay. Now what is P? P is called partition, right? Partition, let me explain it. Basically, we had defined that A is less than T and B is greater than T, right? So this T is called a parameter. So basically we are defining the parameter for different sections of a curve. Suppose this is the curve. So in this we are defining different parameters, right? So for example, corresponding to Z1 we will have a T1, right? Corresponding to Z2 we will have some T2 and somewhat like that, okay? So that is why for every Z we have a T, right? Or I should say that for every T we have a Z over here, right? So that is why we are defining it like this, that this is T0, this is T1, this is T2 and so on till Tn, right? And we have said that Tn is equal to B, right? Okay. So corresponding to the partition P, curve C is divided in n smaller arcs, right? Which is denoted as sigma k. That arc is denoted as sigma k, which is from zk minus 1 to zk, where k is equal to this, right? So we can see over here that z of k is equal to z of t k, right? So basically this value of function, this is basically z1, or we can say z at t1, right? That is what I have said when I said about partition. So basically we have divided the curve into n different regions, right? So yeah, let zeta k is equal to z of sk, where sk is lying between t of k minus 1 till t of k. So basically this curve is represented as zeta 1, right? From z0 to z1, and from z1 to z2 it is zeta 2, right? Understood? So basically that curve is known as zeta over here, okay? So we have defined it like this, correct? Now we have defined something called norm of a partition. When norm of partition is basically, suppose it is basically this partition value, right? So what does it mean? Well, it actually means we are finding the maximum value of the partition. So maximum value of the partition will come from this difference, right? Okay. So what we are doing next is that we are defining this partition, the number of partitions, as infinite. Why? Because why infinite? Because the more numbers you have, the more close you get to the curve, right? Understood? That is why. It is simply what you have studied in your 12th grade, nothing new in this. So that is why I'm a bit fast, because we will discuss after these questions. Okay. So basically it is this, okay. So we have choose that n is tending towards infinity in such a way that the norm of partition is tending towards 0, right? Okay. So basically if there are infinite terms in a curve, then of course the partition will keep on decreasing and there will come a time that it will tend towards 0, right? Okay. Simply if you are just increasing the number of partitions, then of course z1 will come close to z0 and so on till infinity, right? If we are going towards infinity, right? Hence the partition value will keep on decreasing and there will come a point where this norm of partition becomes approximately 0, right? Okay. So norm is the maximum that I have told. Okay. So yeah, now this term, this is the sum. Can you understand it? Well, over here it shouldn't be infinity for now. See, it is basically the region, the area of this curve, right? Basically, if I try to define in terms of the real numbers, then this represents the area under the curve. If I talk about in real terms, but in complex it is bit different, but don't worry. So for now, I'm just telling, when you are integrating this, then what is f at zeta of k? Let's understand it this way. So f of zeta k will represent the function value from z0 to z1, right? Z0 to z1, okay? Times the difference. So basically, this curve and this value, right? Okay, so basically kind of the area of this region, right? But of course it is the idea of real numbers, but to understand this I am just introducing it in complex number, but that is not required at all, right? But basically this is the idea, okay, the idea of real numbers only, okay. So that is why we are taking the sum from k is equal to 0 to n and then this quantity. So basically we are trying to evaluate at every zeta, right, at every arc, right? Okay, now if line SP this it exists, then f is said to be integrable, and as the norm of partition tends towards 0, that is n is tending towards infinity, this expression evaluated at the norm of partition at 0, it will be equal to this integration. And if C is a closed curve, then this will represent like this, okay. So in a nutshell, what I've done is that I've just taken different arcs and then I've applied the summation over different arcs over there, right? And from there we got this expression, and from that if I set the norm as 0 tending towards 0, then this expression will be basically k is equal to 1 to infinity, nothing else, right? It means k is equal to 1 to infinity if I remove this limit sign over here. So then this thing is called the complex integral of f of z, right? So that is the basic idea, and I am sure that you have already studied it in your 12th grade, so I don't think so that I should discuss much on it, okay. Now let's discuss some of the properties and all, right? Let me list this. So this is the complex integration, right? Now we all know that z of t was equal to x of t plus I y of t, right? So let's convert it into parameterized form. So z dash of t is x dash of t plus I y dash of t, right? Correct? Or you can say it as dz by dt is x dash of t plus I y dash of t, correct? So we can say this is the integration, the complex integration f of z. This is dz. It is equal to complex integration f of z d, or we can just substitute over this value x dash of t plus I y dash of t dt, right? And it is going from a to b because t was going from a to b, right? We are defined it like this, correct? Okay, now let's see some of the properties. First property, linearity, right? Linearity, right? So basically the complex integration of some alpha f of z plus beta g of z is equal to alpha f of z dz plus beta g of z dz, right? What is the second property? Negative c f of z dz is negative c f of z dz, right? Okay, let me tell you that c is curve joining suppose z0 to z1, right? And minus c is the curve joining z1 to z0, okay? Just the difference of direction. Now c1 plus c2 f of z dz is equal to c1 f of z plus c2, of course dz also, plus c2 f of z dz, right? This expression. Now there is something called ML inequality, right? So if L is the length of contour, how we calculate the length of contour? Basically this integration, okay? So it means it states that this value, this whole mod f of z dz is less than equal to the quantity f of z dz, right? Now if f of z has a maximum value, the mod of f of z, if suppose it has a maximum value of m, right? So we can set it equal to like this, m, this complex integration, right? So it is less than ml. So it means that this integration f of z dz is less than equal to ml, right? Okay, so this is called ml inequality, where l is the arc length, l is the length of the contour, right? Contour C. Okay, so yeah, that is it. Now yeah, let me write it like this, that m is the maximum value in a to b of f of z, right? Okay, that is it. Okay, so now let's see some other concepts. Okay, so now let's solve this question. It states we have to find this complex integration from z is equal to 0 to z is equal to 4 plus 2i along z of t is equal to t square plus iota t, right? So we are given this curve. Okay, okay, so this is the curve. So we all know that z bar dz, this is the question which we are given. So z bar is equal to x minus iota y, correct? And what is dz? It is dx plus iota dy. Remember, we had proved right there, over there. We had said f of z is equal to u plus iota v, and dz is dx plus I dy. Remember this, which we had done, right? Okay. So this is that is the expression, and now we can just substitute the value. So what is the value of x? It is t square minus t I, of course, because we already had an item over here. So the value of y is t over here, right? Y is equal to t. Okay, so I can write it like it, correct? Okay, now what is dx? Dx is equal to 2t dt, right? Because dx is equal to 2t dt, simple differentiation, and dy is equal to dt, correct? So it is equal to 2t dt plus I dt, correct? Okay, so now let's substitute the limits over here. So what will be the limits? Well, t is going from here. We can say that let me write over here. Z is equal to 0 comma 0 to z is equal to 4 plus, that is 4 comma 2, and z of x comma y is equal to t square comma t, right? Hence we can say that this is the value of t, this is the value of x, this is the value of y. Hence t is going from 0 to 2, right? From here 0 to 2, this is the value of t, right? So it is going from 0 to 2, right? Okay, so now let's just solve it. 0 to 2, t square minus it 2t plus I dt, right? Now just multiply it. 0 to 2 of the point 2t cube plus it square minus I 2t square plus t dt, right? Now just evaluate this expression. You will get 2t raised to the power 4 divided by 4 plus it cube divided by 3 minus I 2t cube divided by 3 plus t square by 2, evaluate from 0 to 2, and just substitute the value. You will get your integral value. Okay, so you will get some a plus iota b over here, right? That is it. So it is just basic integration only. Just the concept is how you convert it from here to here. That is it. Nothing more in this. Okay, so let's see another example. You will understand more. Okay, so the question states this integration f of that is 3z square dz from z is equal to 0 to z is equal to 4 plus 2 iota along the line from z is equal to 0 to 2i, right? Z is equal to 0 to 2i, right? Along this line. And of course, whenever you are evaluating this integration, then of course you will be given along which curve you are going, right? Okay. From z is equal to 0 to 2i, right? And then the line from z is equal to 2 iota plus 4 plus 2i, right? So now you can see that there are two curves. First curve is this one, C1, and this is C2. So basically we have to evaluate this C1 plus C2 f of z dz. Now if you remember that I told you the property, if you remember, it was C1 f of z dz plus C2 f of z dz, right? If you remember this property. So there are two curves, so we have to apply this only. So first of all, let's evaluate for C1 and then we'll evaluate for C2, right? So let's calculate it. So the region is, the curve is, let me draw it. This is X, this is Y. So the line joining, line from Z is equal to 0, Z is equal to 0 to 2I, that is over here. This 2I, right? Okay, correct. This is the Z plane. Okay, and then the line from Z is equal to 2I to 2I2, 4 plus 2I, that is this. So this is 4 plus 2 iota, right? Okay. So this is the first curve and this is the second curve, right? What is the equation of first curve? Well, so C1, so it is integration in the C of the quantity f of z dz, it is equal to 3z square dz, right? Now what is z in C1? Well, z is equal to iota y because it is along vertical axis, right? Hence, it is equal to 0 to 2, the integral 0 to 2, because it is going from 0 to 2, right? Of the quantity 3 iota y squared I dy. Why there is no dx term over here? Because there is no change along x axis, right? That's why. Hence, we have this expression as negative 3 iota integral 0 to 2 y squared dy minus 8i, right? So this is the integral for C1, right? This is the value of integration for C1 is negative 8i, right? Okay. Now for C2, what is the expression for curve in this? Well, it will be x plus 2 iota by z is equal to x plus 2 iota, because of course it is along the, it is already in y axis by 2 units, so of course we have to add 2i, right? So it is x is variable, plus 2i because 2 is the constant over here in y axis, right? So now let's evaluate this integration. So it is going from 0 to 4 x plus 2 iota whole square 3 times whole square dx, right? Of course there is no change along y axis, so there will be no dy term over here, right? Okay, so 3 and then this integration x square plus 4 ix plus, let me write here, minus 4 dx, right? So it is equal to 3 times the integral x cube by 3 plus 2ix square minus 4x evaluated from 0 to 4. So it is basically 64 by 3 plus the quantity 32i minus 16, right? Minus 16. Okay, so it is basically 64 plus 96 iota minus 48, right? So what is 64 minus 48? Well, it is equal to 16, right? 16 plus 96 iota, right? Correct. Okay, now this is the value of integral in C2, right? So we all know that integral C1 plus C2 is basically C1 plus C2, right? Hence the final value of this integral will be the sum of this and this, so it will be equal to 16 plus 96 iota minus 8 iota, hence 16 plus 88 iota is the final answer. Understood? So basically this is the idea. Basically that is why I have told this identity. It is very much important to learn it and to understand this, right? So basically this is how you solve such kind of problems, right? Now let's move to some other concepts. That is, now we are going to move to Cauchy theorem, right? Now let's see Cauchy theorem. Cauchy theorem, okay? So let me write the statement first of all. If f of z is analytic with a continuous derivative in a simply connected domain D and C is closed contour, C is closed contour lying in D, then we have f of z dz is equal to 0. Did you understand anything? Well, suppose this is it, and inside you have suppose a contour. So if it is analytic, right? If fz is analytic with a continuous derivative, yeah, okay. So if fz is analytic with a continuous derivative in a simply connected domain D, and C is closed contour lying in D, right? So it means that fz is analytic everywhere. Then in that case, this integral, suppose this C, this integral will become z, right? Will be equal to 0, right? So this is the Cauchy theorem. Okay. So you can prove it also. Let's prove it, right? Let me derive it also. Let me erase this first of all. So let's see the proof. Well, we all know that f of z is u plus iota v, right? Okay. Okay. Now we know that this integration f of z dz was equal to what? It was equal to this integration u plus iota v dx plus I dy, correct? If you remember, we had already proved this. So it was equal to, let me write the result only, u dx minus v dy plus iota the integration c v dx plus u dy, right? Okay. Now if you remember Green's theorem, basically this is a line integral. So if we have to convert it to a surface integral, then we use Green's theorem, right? So it states this expression, m dx plus n dy is equal to, in R, the region R, del n by del x minus del m by del y dx dy, right? So this is Green's theorem, right? Okay. So this is m dx and this is n dy, right? So over here m is equal to u and n is equal to negative v, and over here m is equal to v and n is equal to u, correct? So just apply over here the Green's theorem. So you will have this value, negative vx, negative uy. Just evaluate this. I'm just writing the result because I have, so that you know Green's theorem. So basically I'm just substituting the values back over here, right? So it does not require that much explanation. It is just I'm substituting the values over here, nothing more. Okay. Plus this integration vux, minus vy dx dy, right? Now we all know that the Cauchy theorem is valid for analytic function, f as an analytic function, and if f is an analytic function, it means that it should follow CR equation, that is Cauchy-Riemann equations. Hence we have u, x and uy, there must be a relation, so it is equal to vy, it is equal to negative vx, right? So it is negative vx, okay? So it is basically equal to uy, so this is uy basically. So uy minus uy is 0, right? Similarly, this expression is also 0. Hence, this is equal to 0. Now we were evaluating this integral, right? So f of z dz is equal to 0. This is the Cauchy theorem. It is valid for analytic functions. Okay. So now let me raise this. Now let's study Cauchy integral formula. Well, if a point is not analytic at any point, then in this case we use Cauchy integral formula. Then at that point the integration is still possible. It will have non-zero integral value. So let me explain it. So for example, it is given like f of a is equal to this value, 1 upon 2 pi iota f of z minus a dz. Okay. Now we can clearly see that this expression is not analytic at z is equal to a. So basically this is the d and this is c, and inside that c there's a point a where the function is not analytic. Then in this case we use Cauchy integral formula. There's is still, in that case, at that point, the value of integral will not be equal to 0, right? Okay. So this we can say f of z divided z minus a dz is equal to pi iota f of a, right? So this is the another way to write this expression. Okay. Now what we can do is that first of all we all know that f of a is 1 upon 2 pi iota in the contour this f of z z minus a dz, right? Now let's differentiate it with respect to a, right? F dash of a is equal to 1 upon 2 pi iota c f of z z minus a whole square dz, correct? So when you take its derivative, the z minus a term goes in the numerator, so it becomes z minus a raised to power negative 1, right? So when you take its derivative, it will become negative, will come outside, so it will become negative z minus a raised to power negative 2, and since a also has a negative term, so it will become positive, so it will be this expression. Now let's take the second derivative. It will be equal to, it will be z minus a raised to power negative 2, right? So it will be 2 by 2 pi I f of z z minus a whole cube dz, right? Sorry. Now let's take the derivative n times. So f any derivative at a is equal to the quantity n factorial 2 pi iota complex integral f of z z minus a raised to power n dz, right? So this is another way of writing this. It is for a general case, right? So now let's discuss some questions to understand this, right? It is like confusing. I also know that suddenly I told so many formulae. Let's discuss the question so you will understand it. Sorry, it will be n plus 1, right? Okay, sorry, it will be n plus 1. Notice over here. Because second derivative had 3 power, so n power will have n plus 1 power over here. Okay? Okay. So let's do this question, this integration where C is a circle first, mod z equal to 1 and mod z equal to 3, right? Okay. So for the first one, this integral e to the power z z minus 2 dz, it will be equal to what? 2 pi iota f of a? No. Why? Because over here the value of mod z is equal to 1. It means that it is a circle like this. 2 will lie somewhere here, 2 comma 0. It means that 2 is lying outside the contour, hence we can't apply Cauchy integral formula there, so it will be equal to 0. Okay? Okay. Now, second one, this e to the power z z minus 2 dz, it will be equal to 2 pi iota f of 3, which is equal to 2 pi iota, sorry, f of 2, 2 pi e square, right? That's it. Understood? So over here we could apply Cauchy integral formula because the mod z value, since the circle was mod z is equal to 3, right? And z is equal to 2 was lying inside that circle, right? It is lying inside that. That's it. Okay. So let's erase this. Now let's see another question. I will not discuss its solution. You can do on your own. Suppose this integral tan z divided by z square minus 1 dz and mod z is equal to 3 by 2, right? Okay. So how you will do this? You can see that there is a 2 power over here. So you will do partial fraction. That is, you write 1 upon z square minus 1 as 1 upon z minus 1 minus 1 upon z plus 1 into 1 by 2, right? Like this you can write. And then you can just simplify this because it will be of the form z minus that form only. F of z divided by z minus a, right? Now it is in the same form where f of z is equal to tan of z. Yeah, over there also f of z was e to the power z. Over here f of z is equal to tan z, right? Correct. And notice since f of z, notice that mod z is equal to 3 by 2. Okay, so we know the region also. Now we can solve it. So both z is equal to 1 and z is equal to negative 1. Both are inside this region, hence we will have to evaluate for both. Okay, let me solve it only. So it will be tan z, that is, it will be simply tan of 1 over here. Let me evaluate this. Tan z divided by z minus 1 plus the quantity minus the quantity tan z divided by the quantity z plus 1 dz, right? So it is basically equal to 1 by 2 is common, 1 by 2. So it is 2 pi iota tan of 1 minus the quantity tan of that is 2 pi I tan of negative 1. What is it? It is equal to plus 1 over here, right? So it will be just equal to 2 pi iota tan of 1, right? That's the answer. Okay, correct. Just check it once. Basically what I've done is that I've taken the partial fraction, and after that I have just write it like this, and then I evaluated. I used the Cauchy integral formula over here and over here also in both the expressions. So I got 2 pi I tan of 1 minus 2 pi I tan of negative 1. So tan of negative x is equal to negative tan x. So I applied that formula and I got this expression. I added them, and since there was 1 by 2 also, so after adding I got 2 pi iota tan of 1. That is it. Simple. Okay. So now let's see another question. So this integral e to the power 2z z plus 1 raised to the power 4 dz, right? This expression, and where c is the circle where mod z is equal to 3. Okay. Is it 0 or is it having some value? Think. Well, we can clearly see that z is equal to negative 1, where it means that a is equal to negative 1 over here, and negative 1 of course lies in this expression, right, in this region. If you remember this expression, f of z, z minus a raised to power n plus 1 dz is 2 pi I f nth derivative of a, right? Correct? Okay. So now over here we have a power 4, right? Hence we have 2z z minus minus 1 raised to power 4 dz is equal to 2 pi iota f nth derivative of negative 1, right? So what is n over here? N is equal to 3, right? Correct. Now we know that f of z is equal to e to the power 2z. Hence f dash of z is equal to 2 e to the power 2z, and f double dash of z is equal to 4 e to the power 2z. F triple dash of z is equal to 8 e to the power 2z, right? Okay. So f triple dash of z is equal to this. Hence f triple dash of negative 1 is equal to 8 e to the power negative 2, right? Hence we have the expression 2 pi iota into the quantity 8 divided by the quantity e square. That's it. Okay. And yeah, one more thing, here was an n factorial also. So n factorial, so it is 2 pi I into 8 divided by 3 factorial into e square, which is equal to what? 8 pi iota divided by 3 e square, right? That's it. There was an n factorial also in the denominator. Okay. So let's move to next topic now, power series. Okay. So let's erase this. Power series, right? Okay. So a series of this form is called a power series. Power series about z is equal to a, right? Okay, where an and a are the fixed complex numbers and z is a variable complex number, right? So n is equal to 0 to infinity a n z minus a raised to power n is absolutely convergent if n is equal to 0 to infinity of the quantity a n mod times z minus a, and this is also convergent, right? So this is called absolutely convergent if this converges, right? So this is the same thing which we discussed in integral calculus also. If you remember, I taken that lecture in probably it's like about 6-7 months back. I have taken that lecture. So I discussed about, not in that, I discussed in sequence series. Sequence series I discussed that. Okay, so you can check out that video if you want to learn more about this. But it's okay if you know till over here. Okay. So now for every power series this n is equal to 0 to infinity a n z minus a raised to power n, there exists a real number r such that this expression z minus a is less than r, right? The series is absolutely convergent, and for so if there exists such r for every such number, then it is said to be a convergent series. And if for every z minus a, it is, if it is greater than 0 for every z, then it is called a divergent series, right? So we'll be checking it using some example. You will understand it using some examples, I mean. Just now it's just theory which I'm just writing for now. If you will, when you will see questions, you will understand it better. Okay, so if you want, you can note this, all this, else it's not necessary. Okay, so over here r is called the radius of convergence of the power series. Okay, so how do we check for the convergence? Well, there's something called a ratio test and a root test, which is similar, which we have discussed in sequence series, right, in first year lectures. Okay, so first of all, let me raise this and then we will discuss a question so you understand it, right? Okay, so find the radius of convergence of the power series summation n is equal to 0 to infinity z raised to the power n factorial, and we have to check for convergence. Okay, solution. So of course it is about z is equal to 0, right? Okay, so n is equal to 0 to infinity, right? So we know that a is equal to 0 over here and an is equal to 1 upon n factorial. If we compare from that form, an z minus a raised to the power n, right? It is just this. Okay, so where an is equal to 1 upon n factorial and a is equal to 0. Okay, now the ratio test, it states that 1 upon r, the radius of convergence, is the limit as n tends towards infinity an plus 1 divided an, right? So it is equal to an plus 1 divided an. So what is an? An is equal to 1 upon n factorial, right? So it is basically 1 upon n plus 1 factorial times n factorial as the limit tends towards infinity. Hence limit n tends towards infinity of the quantity n factorial divided by n plus 1 factorial, it is equal to limit as n tends towards infinity of 1 upon n plus 1, which is equal to 0, right? Hence r, 1 upon r is equal to 0, hence r is basically tending towards infinity, right? Now to be convergent, it should be mod of z minus 0, this z minus 0 less than r, and of course if r is tending towards infinity, hence it is convergent, convergent for all z, right? It is convergent for all z, since of course mod z is less than infinity, hence it's of course always convergent, right? Okay, so now let's see another question. So this is the question, n is equal to 0 to infinity 3 plus iota raised to power negative n into z raised to power n, right? So now in this we'll apply root test. Why root test? Because we can see a power of n over here. Let me explain. Root test is basically limit as n tends towards infinity mod of an 1 upon n, right? This is equal to again 1 upon r, right? So we can see a power of n over here, so we will apply this because it will of course cancel out the power of n, right? Hence we have limit n tends towards infinity of the quantity 3 plus iota raised by negative 1 mod, right? So it is limit n tends towards infinity raised by 1 upon n mod of the quantity 1 upon 3 plus iota raised by n 1 upon n. So n and n gets cancelled. So it is basically equal to 1 by root 10, which is equal to 1 upon r, right? Hence r is equal to root 10. Now again a is equal to 0, since z minus 0, since z is equal to z minus 0, hence a is equal to 0, right? Hence mod of z minus 0 is less than root 10, and for these values it will be convergent, right? And if mod z minus 0 is greater than root 10, then for these value it will be divergent. So this series is convergent if mod of z is less than root 10. Okay, understood? Okay, now let's study Taylor series, right? So basically you must have studied Taylor series in functions in several variables, I guess, in single variable or several variables, I don't remember. I had I taught that in first year, right? If you remember. So it is that only, but in complex numbers. So f of z is equal to summation n is equal to 0 to infinity a n z minus a raised to power n, right? Where mod of z minus a, of course, is less than some delta, okay? So an is equal to f nth derivative of a divided by n factorial. It is called Taylor's coefficient, okay? And delta is the distance of a to the nearest point of c, right? So basically delta is the distance of point a to the nearest point of c, right? Okay. So basically over here we have certain other formulae. Yeah, if a is equal to 0, then it is called Maclaurin series. Maclaurin series, right? Maclaurin series, okay? And if d, if you remember what is d, I defined d and c, if you remember, right? So if d is a disk, then delta is called the radius of convergence of Taylor series, right? Let's discuss that now using question. So f of z is equal to 1 upon 1 minus z. So you have to find the Taylor series about z is equal to 0, okay? So f of z is basically this, n is equal to 0 to infinity of the quantity f nth derivative 0 divided by n factorial times the quantity z minus 0 raised to power n, right? Okay, simple. Now what we can do is that f of z we can write, since we know that it is equal to 1 upon 1 minus z, right? Hence f one derivative of z is, it is equal to 1 upon 1 minus z whole square. F second derivative is equal to 1 upon 1 minus z whole cube raised to the power 2, right? Correct. Hence from this we can say that f nth derivative of z is equal to n factorial divided by 1 minus z raised to power n plus 1. Correct? Right? You can see yourself, right? Hence f of z is equal to this summation n is equal to 0 to infinity. What is fn of this quantity? It is and of course evaluated at 0, then it will be n factorial itself, right? So it is n factorial divided by n factorial times z raised to power n. So it is equal to 1 plus z plus till so on till infinity, right? So this is your expression over here. Now how you find the convergence over here? Well, you remember 1 upon r is equal to the quantity this mod of an plus 1 divided by an, right? This as limit n tends towards infinity, right? Of course this is inside a mod, if you forgot this is inside a mod, right? So now we all know that what is an. Well, an is basically f nth derivative at 0 divided by n factorial, right? Hence an is basically equal to n factorial divided by n factorial, which is equal to 1. Hence this is also equal to 1 and this is also equal to 1, right? So it is equal to 1. Hence r is equal to 1, right? So this is the radius of convergence for Taylor series, right? Hence if mod z minus 0 less than 1, then this is convergent, and if mod z minus 0 is greater than 1, then it is divergent, right? So for here it will be mod z less than 1, right? Okay, so this is the basic idea of Taylor series, right? So now let's move to next concept. Now let's study Laurent series. Laurent series. So basically it is of the form fz is summation n is equal to 0 to infinity an z minus a raised to power n plus the quantity n is equal to 1 to infinity bn divided by z minus a raised to power n, where bn is equal to a subscript negative n, right? Okay, so let's see that question only. F of z is 1 upon 1 minus z, okay? We have to write its Laurent series for mod z greater than 1, right? So in that case when we were forming Taylor series, then in that when mod z was greater than 1, we said that it is divergent, but in this case we can still solve it. Let's see how. Well, either you apply this formula, or you, if you remember, 1 plus x raised to power negative 1, what is it equal to? And what is 1 minus x raised to power negative 1? It is equal to, well, it is equal to 1 plus x square and so on, right? Correct? And if I talk about this expression, it is 1 minus x plus x square minus x cube and so on, right? If you remember this expression from the binomial expansion, right? So similarly, okay, so over here what we'll get, 1 upon, we can take z as common, 1 by z minus 1, right? Because if mod z is greater than 1, then 1 upon z, 1 upon mod z will of course be less than 1, correct? Okay, hence this is negative z taken as common, 1 minus 1 upon z, right? And it can be written as negative 1 upon z times 1 minus 1 by z negative 1, right? Okay, so now just apply this expansion. You will have negative 1 by z times the quantity 1 plus the quantity 1 by z, 1 by z square, 1 by z cube and so on till infinity. So it is negative 1 by z, negative 1 by z square, negative 1 by z cube and so on till infinity. And that is the expansion, that is the Lorentz expansion for 1 upon 1 by z for mod z is greater than 1, right? Okay. And we can say one more thing, that a n over here is basically 1 upon 2 pi I integral f of z, z minus a dz, right? That is it. Okay. You can prove it also, because we all know that a n was equal to what? N plus 1 also. So you can prove it also if you want using Cauchy integral formula, right? Okay, so now let's move to next topic. Now zeros of a analytic function. Well, let f of z be analytic at z naught, right? Then z naught is called the zero of f of z if f at z naught is equal to 0, right? Now there's something called order of 0 at z naught, right? So suppose if f of z is equal to some w, right? So w is equal to f of z, right? Okay, so if f at z naught, if f at z naught is equal to 0, and suppose f dash of z naught is also equal to 0 till some f of k derivative of z naught is equal to 0, and suppose after that k plus 1 derivative at z naught is not equal to 0, then so the order of 0 at z is equal to z naught is k plus 1 over here, that is the derivative value. Okay, so for example f of z is equal to z square, hence f of z naught, that is f of 0, is equal to 0, f dash of 0 is equal to z at 0 is equal to 0, f double dash of 0 is equal to 2 at 0 is equal to 2. Hence over here it is 1 plus 1, that is 2 is the order of derivative over here. Sorry, order of 0 over here at z is equal to 0. Okay, so now let's see some of the concepts. Basically now we are going to understand what is singularity, right? You must have heard it like in black holes also and many other concepts of physics. So let's discuss that now. So what is a singular point? Let me write its definition. A point z naught is called singular point of a function f of z if fz is not analytic at z naught. Maybe it is not defined, okay, may even be undefined at z naught also, right? So basically what I want to say is that if a function, sorry, please don't mind my writing, it is just for to tell you all what is it. It is just not for any notes and all. We will discuss everything using questions. I was just writing it for like that. Okay, so basically maybe it is undefined also, but is analytic at some point in every neighborhood of z naught. The function is said to have a singularity at z naught, right? So basically, if the function is not analytic at that particular point, basically, if suppose z is equal to a, that is it, then that point is called a singular point. Okay. Now singularity can be of two types, like isolated and non-isolated. Isolated singularity is basically okay. We will not discuss it like that. We will discuss it using questions, right? So I need to tell you one thing, that isolated singularity is divided into three categories, right? Which I will be telling using questions, right? So let's see them. So if you remember, f of z was equal to summation n is equal to 0 to infinity a n, the quantity z minus a raised to power n plus the quantity n is equal to 1 to infinity b n divided by z minus a raised to power n, right? This expression, this was Lorentz series, right? So this is called the principal part, okay, okay, of at so if suppose I am naming it as p, okay, so if p has no terms, if p has no terms, then it is called as removable isolated singularity, okay. If p has finite terms, then it is called as a pole singularity, right? And if p has infinite terms, then it is called essential singularity, right? Okay. So removable singularity, basically suppose sin z divided by z, right? Limit as z tends to 0, right? So of course it is 0 by 0, so it is so there is a singularity at z is equal to 0, right? But if you use the L'Hospital's rule, then you will get limit as z tends to 0 cos of z, which is equal to 0, sorry, which is equal to 1. Hence hence this function has become analytic at z is equal to 0, right? So it was a removable singularity. And if you want to check it using the principal part, you know that sin z is z minus z cube by 3 factorial plus z raised to the power 5 divided 5 factorial and so on. Hence sin z by z will be 1 minus z square by 3 factorial plus z raised to the power 4 divided by 5 factorial and so on. Now we can notice that there is no 1 upon z term in any of these expressions, right? Hence it has no p term. Hence if it has no p term, that is a removable singularity, right? Which we saw it, right? Now let's see pole singularity and essential singularity, right? Okay. Let me define also. Suppose there is a function f of z is equal to phi of z divided by z minus a raised to power m. Then this denominator, when set it equal to 0, when set as 0, then it has a pole, right? The value of pole is a over here. Hence what is the order? The order of the pole is equal to m. How do we calculate the order of a pole? Well, limit z tends to some z naught, z minus z naught raised to power some k, f of z. If this is a finite value, then this k is called the order of pole. So similarly over here, if I multiply by z minus a raised to power m, then this expression will get cancelled, and then I will get phi of z at 0, sorry, z naught, right? Hence this will be the order of this pole is m, right? So if this is finite and limit z tends to z naught, f of z is infinity, then this is called a pole in singularity, right? And if in essential singularity, if this expression is not finite, it is tending towards infinity, then this is called an essential singularity. In that case, you will have infinite singular points, sorry, infinite terms in principal part of f of z at z is equal to z naught, okay? So this is a basic idea, that is the idea basically of the singularity over here, right? So now we will do some questions, and I will tell you the difference between isolated and non-isolated singularity. For example, if we have suppose a function tan z, right? Tan z. So it is sin z divided by cos z. So at what points it is not defined? Well, at 0, sorry, when z is equal to plus minus pi by 2, when plus minus 3 pi by 2, and so on, the odd multiples of pi, right? So it is not defined at particular points, right? So if that is the case, at particular points, there are different points, the function is not defined, then it is called an isolated singularity. And if there are multiple points in the neighborhood of, suppose neighborhood of pi by 2, there are multiple points near that pi by 2, then in that case we say that that is an as a non-isolated singularity, right? So there is a difference between isolated and non-isolated. So basically isolated, it is isolated. Basically it is at different points, and in non-isolated it is like it is like very close. Okay. So now let's see some questions. Okay. So suppose this is a question. So I have already discussed the question for removable singularity. So suppose f of z is this expression 1 upon z times z minus 2 raised to power 5 plus 3 upon z minus 2 whole square, right? So of course it has singularity at z is equal to 0 and z is equal to 2, right? Okay. So we can clearly see that it is a pole singularity. How? Just apply limit as z tends to 0 of the quantity z times. Okay, now it is a simple pole. What is a simple pole? When its order is equal to 1. So z is equal to 0 is a simple pole, and z is equal to is a pole of order 5, because you will need z minus 2 raised to power 5 to cancel both the terms. Okay. Okay. This multiplied by f of z, so it is equal to limit z tends to 0. When you multiply by z, you will have 1 upon z minus 2 raised to power 5 plus 3 upon z minus 2 raised to power 5. So it is equal to 1 upon 32 plus 3 upon z minus 2. It will be negative this value. Z minus 2. What is z minus 2? It is negative 2 whole square is equal to 4. So that is the expression. You can solve it further, right? Now if limit at z tends to 0, so 2, z minus 2 raised to power 5 f of z, right? So it is equal to limit z tends to 2 of the quantity 1 by z plus 3 times z minus 2 raised to power 3. So this is 0 and this is 1 by 2, right? So now you understood. Okay, so if this is the expression, so this is a finite value and this is a finite value over here, right? Okay, hence it is a pole singularity. Okay, so now let's see essential singularity. Question, f of z is equal to e to the power 1 by z, right? Okay, now we know that e to the power z can be written as 1 plus 1 by z plus 1 by 2 factorial into z square plus 1 by 3 factorial into z cube and so on till infinity, since e to the power x is equal to 1 plus x square by 2 factorial and so on and so, right? Hence there are infinite principal power terms over here, infinite terms in denominator. Hence it is an essential singularity, right? Okay. Now if you remember, I defined tan z, right? So in that it was sin z by cos z, right? So if z was equal to 2n plus 1 divided by 2, or we can say pi by 2, right? If it was an odd multiple of pi by 2, then the function was undefined, right? Hence, is it a pole? Let's check. Limit as z tends to zn. Suppose this is zn, okay? Of the point z minus zn times the function this tan z, right? This tan z divided by cot z, it will become cot z, okay? F of z is equal to tan z, hence it is equal to 1 upon cot z, right? Okay. So now if you apply L'Hospital rule, because if z tends to zn, then it will be 0 by 0 case, right? Hence we will have limit as z tends to zn of the quantity 1 upon negative 1 upon cosec square zn, right? If you substitute the value also, so it will be equal to negative sine square zn. Now at these values, the sign will become what? It will be 1 only, so it will be equal to negative 1, right? Plus minus 1 squared, it will become plus 1, right? So plus 1 multiplied by 1 by a negative 1, it will be equal to negative 1, okay? So it is a pole. So all these Zn are the simple pole, right? Okay, so it is a pole singularity, right? Understood? Okay. Now isolated singularity at z is equal to infinity. Basically, if you have to check for isolated singularity at z is equal to infinity, then just check for the isolated singularity in this case. Z is equal to 0. Rest everything will be same. If this will be isolated singularity, then this will also be isolated singularity, right? Okay, so if the pole exists at some value in this case, so pole will exist at same value in this case also, right? That is it. Now let's study something called residue, right? So let's start with the question itself. E to the power z square divided by z minus iota cube. So we will solve this question. So we have to find the singularity and residue at those singular points, okay, of this function. So residue of a function f of z at some z naught is given as 1 upon m minus 1 factorial limit as z tends towards z naught of the quantity dm minus 1 at derivative dz m plus m minus 1 z minus z naught raised to the power m f at z, right? This is the value, okay? If z if f of z, sorry, has m poles at z is equal to z naught, okay? And yeah, residue at z of f of z at infinity is equal to negative the residue value of 1 upon z square function at z, sorry, function at 1 upon z and at 0, okay? So this is how you calculate the residue at infinity, and this is how you calculate the residue at any general point, right? So instead of where you have z, z is tend to a z naught, just substitute 0 over here and change the function as this, okay? Okay, so this is what is required in case of residue. This is basically the question. This is basically the theory. But what exactly is the residue? Let's discuss that. Remember the Laurent series summation as n is equal to 0 to infinity a n z minus z naught raised to the power n plus summation from n is equal to 1 to infinity of the quantity b n divided by z minus a raised to the power n, right? So B1 is called the residue of function at z naught. B1 is called the residue. Okay. So now let's start with the question. So this is the question. Okay. So of course over here z is equal to iota, right? This is the pole. Okay. Of order 3, because we can see there is a 3. Okay. Hence we have the residue f of z at iota is 1 upon 3 minus 1 factorial d2 by d as dz square, right? Of course there should be a limit also, limit as z tends to iota d2 by dz square z minus iota whole cube f of z, right? Where f of z is equal to ez square divided by z minus iota, right? Cube. So this and this will get cancelled. So we will have 1 upon 2 limit z tends to iota d2 by dz square e to the power z square, right? Okay. So now you can just differentiate it. You will get negative 1 upon e, right? This is the value of residue. Okay. And this is the pole singularity. Okay. Now let's see something called Cauchy residue theorem, right? So let f of z be an analytic function inside and on a simple curve contour C except for the isolated singularity z. Okay. So suppose if f of z is an analytic function, right? Inside or on a curve, okay? Except it has singularities inside C at z1, z2 till zn. Then this integration f of z dz is equal to 2 pi iota summation of the residue of f of z comma zk, right? Okay. Okay. So this is it. Okay. This is the formula, the summation of all the residues of these values. Okay, at these values. For example, this question integration mod z minus 1 is equal to 1 by 2 dz divided by the quantity z square minus 1. Hence we can just see that z is equal to 0, z is equal to plus minus 1. So these are the simple pole, this is the pole of order 2. Now this is the region. Now which values lie in this region? Well, this is a circle, right? Centered at 1, and it is like this. Okay, so over here it has a value 3 by 2, and over here it has a value of what? It has a value of 0.5. Okay, correct. So now 0, of course 0 does not lie over here, and we can see that negative 1 also does not lie over here. Hence only 1 lies in this region. So we have this integral is equal to, the limit is equal to 2 pi I residue of f of z at 1, right? Now residue of the quantity f of z at 1 is basically equal to z limit as z tends to 1 of the quantity z minus 1 times the quantity f of z, right? Okay, you remember the formula, 1 upon m minus 1 factorial times the quantity, the limit as z tends towards z naught of the quantity dm minus 1 divided by dzm minus 1 times the quantity z minus z naught raised to the power m times f of z. So if m is equal to 1, then it converges to this. Basically it becomes this expression, right? So it is equal to, from this we can say, limit z tends to 1 1 upon z square z plus 1, so it is equal to 1 by 2. So this becomes 2 pi I into 1 by 2, which is equal to pi I. So this is the integral value of this. Okay, so this was all the concept in complex integrals, and I hope so that you understood something from this video. And if you did enjoy this video, then please do like, share, subscribe my channel, and please support this video. And yeah, this was a one shot, so of course I did not cover many questions in this. I covered all the concepts in this video, and I tried to discuss all different types of questions, but of course I could not discuss many deep questions over here. But I can say that if you watch this lecture, you can cover your basics easily, and after this, if you, it's on your practice, right? And of course, if you want a detailed topic wise videos, you can just tell me in the comment section. I will make a detailed topic wise video, so in that I can cover everything, right? So till then, bye bye, take care, and all the best.